Apex is performing in a joint effort STTR with the University of Notre Dame and AFRL in the evaluation of hypersonic testing and testing methods using digital engineering. In both of the tests that we will be performing at both Notre Dame and AFRL, we will be using the DX Plus digital engineering platform for integration of different measurement types, as well as CFD simulations and high-speed video. We'll be using this platform for both real-time analysis as we're performing the test, as well as post-test analysis, analyzing the data after the data has been collected. In these tests, we'll be evaluating the methods for testing in hypersonics. Specifically, we'll be performing a direct connect method at the University of Notre Dame and a Freejet testing method at AFRL. The test article that we will be evaluating is a gooseneck style inlet or diffuser. The geometry and the definitions were provided by a prestigious vendor. We will be evaluating two test article geometries, a geometry that was manufactured by the University of Notre Dame using traditional manufacturing methods and will not contain a forebody. So it will just be the inlet or diffuser directly connected to instrumentation. At AFRL, we will be using an additively manufactured 3D printed test article. This will include a forebody and will be in a Freejet stream in the testing. Both the test articles will include a window. The window will be used for visualizations of Schlieren. At the University of Notre Dame, we'll be evaluating a direct connect method. The direct connect testing allows for a wider range of flight conditions, specifically higher pressure ranges and higher stagnation temperature ranges. It also provides a more direct control of the airflow within the inlet. Direct connect testing is normally cheaper than traditional Freejet testing. This is normally because the Freejet testing requires the use of a facility. Direct connect testing can use on-hand testing setups to directly connect the test article. At AFRL, their testing facility at AEDC, we will be performing a Freejet test. Freejet testing requires a dedicated testing facility, so this is a standard testing facility available at AEDC. Freejet testing ultimately allows for dynamic control of testing conditions, specifically angle of attack and free stream Mach number. In Freejet testing, we can also test with the forebody and analyze the effects that the forebody has. The simulation of the flight conditions are able to be analyzed as a whole with the entirety of the test article. What we're looking for in these tests is ultimately the inlet performance given the range of the testing conditions. So in the Freejet case, we will be changing angle of attack, we will be changing the Freejet stream Mach number. But in Freejet testing, we're limited to the ranges of temperature and the ranges of pressure that we can actually analyze for the test. One of the items that we're looking for in these tests is what's known as the unstart condition. So what is the unstart condition? In hypersonic flow, we are not able to combust air at hypersonic speeds. So the purpose of the diffuser, or the inlet, is to slow down the airflow to a subsonic level. Once it's at a subsonic level, we are able to provide a fuel-air mixture and then ultimately combustion. Whenever we do this, this introduces a shock train in the inlet. So as it moves from hypersonic flow to subsonic flow, you will see shock trains within the inlet. If the shock train moves forward, this will cause a back pressure and ultimately cause what is known as an unstart condition. The unstart condition causes combustion to no longer be able to occur and ultimately a failed flight vehicle. So stay tuned. We are scheduled for these tests in October and January, and we'll be posting results and findings comparing both of the tests that were performed. And if you'd like a deeper dive into the differences between Freejet and direct connect testing methods, please see our white paper, which is now available on our website.